Now that we've covered the elements in the Hammer framework, we're going to take a look at the other common concurrency framework in Android, which is called AsyncTask, which turns out to be much more interesting in a whole bunch of different ways than the Hammer framework, for reasons I will hopefully be able to convince you of. If nothing else, the patterns are more interesting, the way it's packaged up is more interesting, the ability to scale it up to do more things is more interesting, and so on and so forth. I'm actually not going to cover this just because it gets us into a lot of low-level detail. If you watch the video that we did for the MOOC, you can show me discussing how AsyncTask is used in Android itself to deal with the asynchronous processing of the call log. But we're not going to talk about that in any detail right now. We'll show another example. We'll show an example in the context of the threaded downloads application. So the first thing to remember about the Hammer framework is that its classes are loosely connected. What that means is you've got looper and message queue and handler and messages and threads, and they all sort of exist, and you can read the documentation. But it's not really clear until you watch these videos or play around with it a little bit that these things all work together, because the interface is very diffuse. There's like 4 or 5 things that you have to understand, and they sort of exist out there in somewhat of a disconnected way. So it's like giving somebody an erector set or a pile of Lego bricks. They're reusable pieces. OK, great. Now, make me a time machine. All right, well, I got to start figuring out how to put those pieces together. So there's a lot of assembly required to figure out how this stuff works. For really simple stuff, it's great, but it doesn't tend to scale up quite as well. So one thing is, in order to make any sense out of this stuff, you really have to understand the patterns like the command processor pattern or the variant of the active object pattern and so on. It's also somewhat tedious and error prone. The pieces are split out a little bit. You have to understand how all the details work. You can forget some things. Java is very forgiving in a lot of ways about memory management and so on. But things like that recycler, the fact that the messages are recycled after handle message returns, that's a subtle issue. And it's easy to get burned by that if you're not careful. In contrast, the classes in the AsyncTask framework are strongly connected. So rather than being sort of a box of puzzle pieces, they have pre-assembled the puzzle pieces for you and left actually probably take one of them out. So you have to fill one of them in, but you don't have to fill in all of them. It's kind of pre-assembled and packaged. And that has some virtues. Now, as we'll see, there's a thing called an async task, and internally it has an executor that runs a pool of threads if you configure it to run in that particular way. The other cool thing about async task is you don't have to know anything about threads or messages or runnables or handlers or future tasks or executor pools, unless you choose to. There's a few things you can customize if you want, but most of that stuff is hidden for you. And they use stuff internally like handlers and other things, but you don't have to be exposed to those things directly. So in some sense, it's a layering on top of lower layer stuff. Another thing that makes it more desirable once you understand what it does is it provides you a smaller surface area. You just have to understand the async task interface and then how to fill in the parts that are left as variants for you to selectively customize. You don't have to understand all these other classes that are sort of disconnected in some way. So the framework itself, there's a very complicated framework, but it's hidden beneath a facade. So all you really see is this execute method, and then there's a bunch of things that you can manage externally, like on post execute, on pre-execute, and so on. But all the other stuff that takes place internally is hidden from you inside the facade. And this is actually a pattern called the facade pattern. And the facade pattern is a gang of 4 pattern that basically says if you have complex frameworks, you may not want to expose all their complexity up to the application developers, but instead you might want to shield them from those complexities via some kind of facade. Can anybody think of an example of facade that we use very frequently when we're programming? Anybody who's taken the operating systems course, for example, you guys are familiar with certain facades. P-threads, yeah, that's a great example. Lawrence?
I mean, C++ is itself just a facade for C code.
You could look at it that way.
It all compiles down to the same stuff.
In some sense, higher level languages are a facade for assembly code, right? By the same perspective. The specific thing I was thinking of, and Colin was close, the operating system call API, right? If you think about what an operating system does, for those of you who's taken 281 or equivalent somewhere else, you know, an operating system has a lot of complicated things going on, right? It's got interrupt handling and hardware, lots of different kinds of devices. You've got various types of memory. You've got processors, you know, caches, lots and lots and lots of very low-level, tedious and error-prone and non-portable stuff. And nobody in their right mind wants to program at that level, right? It's very low level. It's like, you know, 1963 or something like that. So instead, you want to use something higher level. And one thing an operating system gives you is the system call facade, right? Which is actually very complicated, but it's not as complicated as programming to the hardware. And then, kind of to take on what Lawrence was saying, you know, as you look at things that layer on top of that, each thing comes along and provides a new layer that tries to shield you from something below it and then expose to you more functionality above it. And so facades, you can think of facades as like those nested, like Russian dolls, you know, or turtles all the way down, or something like that, right? You know, it's this concept that gets applied at multiple levels of abstraction. All right, so let's talk more about async tasks now that we've kind of talked philosophically about layering. There are two different types of methods in async tasks. One type are public methods, and these are the things that are invoked by applications. And there's really just a couple of them. There's execute, where you give it something to run, and you can either do execute or you can just pass in a string. And there's also something called cancel, and you can basically use it to shut something down. Cancel is sort of the async task equivalent of interrupt on a thread. We'll talk a bit more about that in a second. So here's basically execute. You can go ahead and give it something to work on. Cancel shuts things down. Then there's also a whole pile of protected methods. Now, these are not invoked by the applications directly. They are selectively customizable, if you so choose, by the application through the magic of subclassing and overriding. And then those methods are what are called by the framework at the appropriate time in the future. And so typically, when you call execute, that sets into motion a bunch of things that end up calling back to the appropriate methods here. And we're going to look at all these different methods in a second. Now, as we go through this stuff, sort of think to yourself, what is the pattern that's being applied here? And we'll see if anybody can guess it. In fact, I probably say somewhere. So to use async task, what you have to do is you have to come along and extend it. So if you have an async task, which comes out of the box from Android, then it's got a couple of methods that are regular methods, like execute and cancel. And then it's also got a bunch of methods that are these hook methods, and they're all prefixed with on. So you can come along and you can selectively override one or more of these things. Now there's a couple, there's one method you almost always do. We'll talk about that in a second. The other ones are pretty much optional. So execute is the main entry point method into an async task, and you can only call it once per async task. And strictly speaking, although you might be able to bend the rules if you're careful, the user interface thread should be the only one to call the execute method. Although I don't think it'll actually blow up if you don't do that, but it's supposed to be called by the user interface thread. And you'll see why in a minute. Well, here you go. This is a template method. So the whole thing is a template method pattern. Gave it away. So execute sets things in motion, and then a bunch of these other methods are called at well-defined places in the processing sequence. On pre-execute is invoked by the framework in the user interface thread to perform initialization that has to take place before we start to run work in the background. And that's why you really shouldn't be calling this thing from anything other than the user interface thread, because if you do, weird things will happen. So you really want to call that from the user interface thread. And on pre-execute runs in the user interface thread. And what on pre-execute usually does is anything that involves interacting with the user that has to run in the UI thread. So for example, you might print out a dialog box, or you might show a toast or something like that, which requires things to be running in the user interface thread. After on pre-execute returns, then work is sent over to a background thread. And we'll talk later how background threads come into existence. But let's assume that there's at least one of them. And The doInBackground method, which you have to override, this is the one you always override, by the way, doInBackground, or almost always override. That then goes ahead and runs in a background method, or it runs in a background thread. You don't know, you don't care. You don't create the background thread. The background thread is created for you by the underlying executor framework. And that's where you can run. And at least in theory, you can block for extended periods of time, although you have to be careful if you don't use the thread pool features of this. As you're running in the background, there may come a point or points periodically where you really want to send some information back to the user interface thread to inform it about something. Like let's say you're downloading a long image or a large image, or you're doing some extended image processing or something, and you want the user to know you haven't forgotten that they exist. So what you can do is you can override the onProgressUpdate method, and when your background thread calls publish progress, that takes the parameter that is passed to publish progress and sends it from the background thread back to the user interface thread where it runs in the user interface thread's context. Now, how do you think it moves the information to be run from the background thread to the foreground thread? How would you expect it does that internally, based on things we've just talked about? Right, it passes a message, right? So it basically uses the message passing mechanism, and it uses handlers, and it does all that good stuff. So it's using all the Hammer framework stuff internally. You're not exposed to what that has to do. The onPostExecute method is called back in the user interface thread after doInBackground has finished and returned its result. So doInBackground returns the result, and that then runs in the user interface thread where it does any post-processing that's required. That might, for example, involve displaying an image, because you've downloaded the image and processed it in the background, and now you're moving it to the foreground thread where it's displayed. OK, so that's one category of things. The next set of things we're going to talk about is the cancel stuff. So you can cancel operations, and that will attempt to stop the task from executing. And I say attempt because obviously if you've already gone ahead and done it, it may be hard to shut it down, right? Anybody here ever see the movie Dr. Strangelove? Classic movie, right? What's one of the messages in that movie that has to do with cancellation? So if you've seen the movie, you know that Jack D. Ripper, who's this insane Air Force general, decides that the communists are putting fluoride in the water, and it's robbing him of his precious bodily fluids and his essence. So he launches a preemptive nuclear strike on the Soviet Union in order to stop them from putting fluoride in the water. Nobody said he was, a very sensible guy, right? But anyway, he starts the bombers off, and they can't bring them back. That's the whole premise of the movie. Once the thing's set in motion, it doesn't stop. And so that's the same issue we have here. Sometimes you can't cancel stuff, but sometimes you can. So when you cancel stuff, then onCanceled gets called back. This is called after cancel is called and after doInBackground is finished. Then the onCanceled hook method gets called. The doInBackground method can also check to see if it has been canceled, much the same way that a thread can call the isInterrupted method to see if it's been interrupted, to check whether it's been interrupted multiple times. So you can go back and watch that if you remember how that works. All right, so that's basically this. All the stuff we just talked about is the template method part of AsyncTask. So you use subclassing to selectively override methods, and then the template methods call back the hook methods at the appropriate point. AsyncTask can also be parameterized by certain types of data to do various kinds of things. There are 3 different things it can do. You can parameterize the type used to process stuff in the background, and that gets passed to the method that's called doInBackground. You can pass it something, and that corresponds to whatever you called execute. When you call execute, you pass in a parameter that gets passed to the doInBackground method as a parameter. There's also progress, which is what gets called back when the onProgressUpdate hook method gets called back. And that's usually like an int or something. And then the final thing is the type of the result, and that's the return value returned from doInBackground and passed to onPostExecute. So doInBackground takes a parameter passed by execute, it runs it, and then when it's done, it returns a result, and that result goes from the background thread to the foreground thread, and it's passed as a parameter to onPostExecute. This becomes much more clear on the next slide, so let's take a look. So here's a very simple example. We're going to define ourselves a download task, which is not unlike what we're going to look at here in a second from the threaded downloads application. The execute method, you can see it down here. We're going to say execute, and we're going to give it a URL to execute. We extend download task. We say async task is extended with a URL, an integer, and a long. And it's then going to go ahead and download the file, which is the URL that's passed in. And if it's a long download, it might want to periodically say how much it's been downloading based on the progress indicator here. And then the last thing it does is when it's all done, it can print back, it can pass back the size of the file, and this could then print downloaded this many bytes on some dialog window. And then this is where we execute it. So we make a new download task, execute, passing in the URL. That goes ahead and calls on pre-execute, which we don't use in this case, but we could to throw up some kind of dialog box or a toast. Then do in background would run, download the file, do whatever it wants to with it, sending periodic updates, and when it's finished, it returns, and onPostExecute gets called to indicate what happened. So that's basically the day in the life of the interactions here. We'll look at this in a little bit more detail later. All right, so now that we've talked about this stuff, now let's go ahead and take a look at how you might actually program it. And we'll do this in the context of our threaded downloads application. And here are the particular classes that we're going to use to make this work. All right, so let's bring this guy back up. And here he is. All right, so you can see that download with AsyncTask is a button strategy, like everything else is. It has an instance of something called download AsyncTask. So if you recall last time, the last one we looked at had basically a message handler here. This one has a download AsyncTask. And here is the implementation of this thing. We have the download AsyncTask method, which is an async task, takes a string, which is the URL, an integer, I don't think we can do much with that, and then a bitmap, which is going to be returned when we're done downloading. Here's the download context. That gets set in the constructor. Set the download context here. Here is the onPreExecute method. This method is what gets called when we start running the async task. As you can see, it just goes ahead and pops up a toast saying we're downloading with the async task. This runs in the user interface thread. Here's the do in background method. This guy goes ahead and downloads the image, and that can block. Yeah.
Remind me what the ... operator is.
... basically means variable number of. So this says that URLs is an array of a variable number of strings. Now, I don't know why they did this, because they just pass in one. so I guess in theory you could pass more, but that's what we do. We pass one in and we use it. But that's what ... means. It's like a variable number of. So it's a variable number of strings. Do in background runs in the background. We go ahead and download the image from that. And then onPostExecute gets called. Notice, by the way, that do in background takes a string and returns a bitmap, and onPostExecute takes that bitmap that was returned from do in background, and this guy runs back in the user interface thread, and he goes ahead and displays the image. Here's how you actually use this thing. So the download and display image method becomes almost a one-liner. We could actually, if it wasn't for cancellation, we could have made it a one-liner. We make a new download task, download async task called mDownloader, and then we say mDownloader execute on the string that was passed in, and that'll go ahead and kick everything off, and those methods get run. And then here is cancel download, and all we do here is we just say we're canceling it, and then we say cancel yourself, and we say, yeah, if the guy's running, you can shut him down. Just go ahead and blow him away. So that's all there is to it. I'm a huge fan of AsyncTask. Once you kind of get your head around what it's doing, it's just so easy to use. And so, in fact, sometimes you can kind of define everything you want right in line. You don't even have to make it a separate class. You just go ahead and subclass things, and you use the anonymous inner class feature, and you override the methods, and it's real clean, real simple. So all other things being equal, I would probably tend to use AsyncTask. I've done a lot of programming with the different flavors of Android's concurrency frameworks, and even when I think to myself, gosh, this is so simple, I could use the Hammer framework, inevitably I convince myself, nah, it's done better using AsyncTask. So I'm a big fan of AsyncTask. Okay, any questions about that? It's just fundamentally object-oriented in its very nature. But there are some pros and cons, and we'll talk about those next time. All right, so let's see. This basically just goes through everything we just talked about. Oh, except that we have the easy button. Right? That's the main difference. It has an easy button. And you don't have to think. The reason why it's an easy button is we don't have to think at all about all this gobbledygook that we had to think about before. OK. So here's some things to think about when you use this particular capability in Android. They allow UI and background threads to communicate with each other. They're more tightly coupled, tightly connected in a good way in this case. You say execute. That goes ahead and gives some work to the executor. So on pre-execute gets called. Execute gets called in the executor. That goes ahead and runs. And then as it finishes, it goes ahead and calls these other hooks that run in the user interface thread context. And all that stuff is shielded from you. Now, I think we'll talk about this in a second. So the good part is that you don't manipulate anything except just these simple interfaces. It also embodies all the great framework characteristics. So we've got inversion of control, except it's much more abstracted now. It's object-oriented inversion of control, not kind of pattern-oriented, deliberately manipulated pattern-oriented inversion of control, which is what the Hammer framework is. Domain-specific structure and functionality. These are things from the domain of concurrent processing in the context of Android, dealing with Android's quirks for its concurrency model. And then semi-complete portion of applications. So here's the interface, and then we come along and subclass and fill in just exactly the things we need to do our work. If we don't need it, we don't have to fill it in. In this case, we use do in background and on post-execute. AsyncTask is used very, very heavily in Android. Now, here's an interesting question for you. There is no AsyncTask-like functionality in Java per se. Right? If you look at Java util concurrent, there's no AsyncTask thing in there. There's stuff that provide the building blocks that AsyncTask uses, and we'll look at some of those in a second. But there's no AsyncTask. Why is that? Why don't they have an AsyncTask-like thing in standard Java? What makes it something that Android has, but Java doesn't? Because at first glance, it seems pretty cool. So what's the very essence of all the stuff we've been talking about with respect to the latest round of concurrency frameworks?
You have one user interface.
Right. So that's another way of saying what you're saying is they're domain-specific properties of Android's design, which are constrained, right? They aren't generic. They're more constrained. And so Java doesn't have those constraints out of the box. So there's no need to put this stuff into Java because Java doesn't have the concept of the user interface thread, right? So there's no need to have a very tightly constrained set of things for that in Java. Android is a, it's a subset, or it's actually a superset, but it's a customization of Java that has these constraints. So it makes sense to build those abstractions into the Android-specific part. But in vanilla Java, it's sort of overkill because they don't have that concept of the user interface thread being a special thing. Now, they have their own windowing toolkit, which probably does something very similar to this. But Java util concurrent doesn't have to know about that. And oddly enough, even though AsyncTask is used all over the place, on progress update is hardly used at all. These are like the only places it gets used. So it's just not as a useful thing. OK, any questions about any of that stuff?